All right, I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to help us to prepare for the test coming up tomorrow, and that we just resolve any remaining questions that there are. Lord, in my prayer, Lord Jesus, amen. So like I said in the announcement, the test is probably, 40% differential equations, 60% series and sequences. So, and I believe I promised that there would be the proof of the geometric series on the test, so that pins down another probably 10% of it. Let's see here. So, problem 1, there are signs of life here for most groups. Some of you missed the half there. Others of you did weird stuff here, just weird stuff. But I don't. There's like an inverse tangent of x squared people had there. I don't understand that. Let's see here. Problem 2. So separate, integrate. Basically is the story for the first two, right? But the second one, if y of 0 is minus 2, so I have to fit that. So I integrate by parts to get this guy here, like so, and then I multiply by 2. And if I plug in y of 0, I get minus 2 squared, which is 4. This is 0, that's 0, so that just gives me c equals to 4. So I get that 4 there. And then I have to put this minus out here because I have the solution's negative. If y of 0 is minus 2, the solution is minus the square root of 4 minus x cosine 2x plus 1/2 sine 2x. Many of you are not thinking about this. You need to think about this. So you can't leave plus or minus. If I ask you for an explicit solution, you got to make a choice. All right? Well, that's not entirely truthful. You don't have to make a choice with the plus or minus situation if I don't give you an initial condition, right? If I just said find the explicit general solution to problem 2, and I hadn't told you y of 0 was minus 2, well then you could have put plus or minus and you've been fine. Yeah.
If you have an initial condition and your y equals isn't like square root, you need to multiply the whole equation by negative. If it's negative, then just leave it like it is.
I don't understand the question.
Because, okay, so like the square root, that's plus or minus.
Uh-huh.
And so I'm assuming you just choose a minus because y is equal to negative 2.
That's right, because
but
y.
if you get something where it's like not the square root of anything and it's not plus or minus, you just leave it like it is, right?
Well, yeah, I mean, it depends on the initial conditions, but if there's no square or something, there might not be a need to.
Only if it's the option plus.
It's because I'm solving for a square. Whenever we take the square root of both sides of a square, that introduces an absolute value, which gives you a plus or minus. That's logically what's going on there. But now this one here, the question was asked of me, is it always this easy? And I said, well, no. If you don't do the pre-calculus correct, it becomes very difficult. That happened to some of you here. You need to simplify this. Exponential of minus 2 dx over x gives you exponential of minus 2 log x, which you bring the minus 2 inside, that gives you absolute value of x to the minus 2 power, which simplifies to 1 over x squared, right? With a plus or minus. Well, no, there's no plus or minus here, actually, but we discussed also in the case that there's a plus or minus, it ends up going away in the multiplication. But anyway, here it should have been 1 over x squared, which then would give you the reverse product rule. Now, some of you went from here to here, but you didn't think through it. If you'd thought through it, you should have realized that your integrating factor was wrong, right? So there's a check here. Think about it. When you think about it, if you differentiate this, you don't go back up to here, that means you calculated your integrating factor wrong. But that's only an error check for you if you actually check it. You got to check it. And then I multiply by x squared to solve for y. Now, technically speaking here, you could have put a box around the step right above, and it would have still been counted right. What is the deal with the ceiling in this room? it's so wacky. Nobody solved problem 4, but this should have been within your reach. We spent, 10, 20 minutes solving y prime prime plus y equal to 0. So if you understood that, you should have been able to mimic what I did there for this problem, right? Because it's the same kind of problem. So to solve y prime prime minus y equal to 0, you make the, the change to the velocity substitution, and then you do the v dv dy trick, and then you separate, you integrate, and then you solve this for v equals to dy dt and do the integral there. You end up with a, I think inverse hyperbolic sign actually for that integral once you solve for v. So I didn't finish it, but you could finish it. It's analogous to y prime prime plus y equal to 0, and the solution turns out to be cosh's and sinches rather than sines and cosines like the other one. Problem 5 is just a really stupidly worded orthogonal trajectory problem. Yeah?
Later, can we go over the v dv dy trick, just to make sure I can remember it? Not right now.
It's okay. There's no time like the present. So if you got dv dt, then all I do in this one-dimensional case, I switch that out for dv dy times dy dt. So this right here is the chain rule. And then, well, what is that? Well, this right here is v. So I put that first usually because I like to say v dv dy because it gives me joy to say that. And that's pretty much the trick. We use the same trick in physics to derive the timeless equation. If you have the acceleration is, let's say, dy, dv dt, where v is, the y velocity, usually we put minus g there in that case, right? Then, my bad, t. Then this trick gives you v dv dy equals minus g. If you separate and integrate, what do you get? You get 1/2 vf squared minus v naught squared equals minus g times the change in y, which of course is vf squared equals v naught squared minus 2g delta y. That, of course, is the timeless equation. This is how you derive the timeless equation, this trick. I mean, there are other ways, but this is the easy way. The orthogonal trajectory problem here, like I said, it's just a stupid orthogonal trajectory problem. Some of you were accusing me of mixing universes. You said that if it had droids, it had to be Star Wars. But I don't do problems about Star Wars because those are unphysical. Ninjas are real. So anyway, just saying. So I reject your Jedi religion. But let's see here. So x squared plus 3y squared equals to 10. You differentiate that. Implicitly, that gives you the differential equation, which this appears as part of the solution set too, right? But then we want orthogonal trajectories, so you flip it and put a minus, which gives me this. Separate, integrate, those are your solutions. I think not many, I don't know if anybody got this, and that's concerning actually. I mean, granted, you probably were just lost in this paragraph of nonsense, but if I had asked the question instead simply as, given x squared plus 3y squared equals to 10, find orthogonal trajectories to this curve, could you do it? If you could, then wonderful. My criticism is not directed at you. If you're still uncertain about that, we'll fix it. It's not a big deal. You could solve this problem. Other question? Yeah.
So just to start off that problem, we have that. So we take the derivative, find the equation, correct?
Yeah, well, right. Since the differential equation is not given here, you have to find the differential equation, which it is the solution for. So yeah, that's the wrinkle there. Problem 6. These are just yep.
Sorry, this is for the orthogonal trajectory.
Uh-huh.
But just so it's easier. So after you do the negative, then you solve for y.
Right. Then I separate and integrate. So 6 over 2 is 3. So dy over 3y, dx over x, and that gives me.
That's not the final answer.
Right here?
Yeah.
No, that's the answer.
Above.
Oh no, I still have to integrate. So, and that gives me 1/3 log. And of course I could solve for y here if you wanted. You get y is like a constant times x cubed, I think. Yeah. But I was running out of space, so I just left it there. All right, so, because after I saw one of you guys wrote the answers on the page, I thought, well, I can get away with doing that too. So I did that for the most part. This one here, the key idea. So okay, so there is this problem was useful because it has uncovered something. For many of you, you are conflating, you are confusing, you are inappropriately identifying the limit of a sequence and the limit and the convergence divergence question. These are separate questions. sequence, converging or diverging, we just have to think about what happens as n gets large, right? So we could have asked these in Calculus 1, changing the n's to x's, right? Although we don't usually typically do stuff like this with x. Okay, fine. But ignoring the plus minus business. You know, these could have been x's and x going to infinity. It would have been Calculus 1 problem, right? But so there's no nth term test, there's no limit comparison test, there's no ratio test, there's no geometric well, there is a geometric sequence test, right? We did prove that. That was in your homework. But, you know, largely speaking, you just either use a combination of the squeeze theorem, or Lhopitals Rule, or just basic algebra like the first one, knowledge about pre-calculus functions, that would be this one in some sense. There's also this indeterminate power trick that you need to know about, right? But there's no convergence divergence theorems here, right? That's for series. Series and sequence are different. A series converges if the sequence of partial sums corresponding to the series converges, right? That's the definition. The limit as n goes to infinity of the sum k equals n naught to n of a sub k. This is what we mean by series converging. So anyway, and I saw that confusion not on one group, but on several groups. That concerns me. That you need to wrestle with that. Am I clear? But, so this one here, basically just look in the dominant terms are the n to the fourth. So this just, after you divide by n to the fourth, top and bottom, you can easily see it goes to minus 3/7. This one here, cosine of n pi is plus or minus 1, but it's squared, so that just squares to 1. So you're looking at exponential of 1, which is e. This one here is actually not an indeterminate form. I don't think it's actually 0 to the 0, I think. Anyway, so I was a little bit not totally confident about it, so I thought, well, I'll just run it through the exponential log trick. And since the exponential is continuous and the log is continuous, I can put an exponential log of this thing, pull the 1 over n out by properties of the natural log, and then this goes to 0, and this is natural log of 1 as n goes to infinity, which also is 0. So you have 0 times 0. There's no debate. 0 times 0 is 0. Not an indeterminate form, actually, after I run it through the exponential log trick here. Anyway, so I get 1, because e to the 0 is 1. Inverse tangent is continuous everywhere, so I can pass the limit inside. And then this character right here, eventually the end of the fourth wins, so that sends this guy to 0. Inverse tangent of 0 is 0, so that's why that was 0. So, yep.
So for these, we do have to show like some intermediate step to like where we got.
I usually just grade the answer here, but it is conceivable I ask a question where I say show your work, yeah. But, you know, in contrast, problem 7 and problem 8, I said show your work. I was pretty in your face about it, right? Like prove. The word prove appeared somewhere here. Oh, here. Now this one, this is just a squeeze theorem, so it squeezes to 0. This one here, there are various ways to see it. The way I saw it was to, and so guys, I was thinking about this. I got myself into trouble in class. You know how I did it? It's really stupid, but for me, for some reason, I get confused if I start by writing the n here in these arguments. I do better if I go 1, 2, 3, da 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 n. Like it makes more sense to me because I read expressions from right to left, and if I'm thinking about the progress of the formula as n is increasing, I got confused because I was trying to think of it right to left rather than left to right. And like this one here, right? If you think about n equal to 1, well, wait a minute, there's division by 0 at n equals to 1. What's going on, right? Well, what's going on is that when n equals to 1, this is not what it looks like, right? When n equals to 1, it stops right here. End of story, right? It's 1 over 1 when n equals to 1. And, you know, when n equals to 2, there's an n minus 2 here. I was basically confusing myself into thinking there's division by 0, but that's nonsense. When n equals to 2, this expression stops right here. Right? So for me, maybe not for you, but for me, a good fix to the confusion I got into class twice in here this semester is simply to write the n factorial from 1 to n rather than from n to 1. Just because I read things and think about things progressively left to right as n is increasing. I mean, they're equal, right? But for whatever reason, this is helpful to me. I don't know. And then the idea here is just, well, how about n over 2, n over 3? You know, n over n minus 1, n over n. These are all what? This makes the denominator what? Smaller than n, if n is greater than or equal to 2, right? So I can replace the smaller denominator with a n, right? And I've done what? I've made the denominator larger. Therefore, I've made the fraction smaller. And I left the first n alone. So I have n. And of course, that is blowing up to infinity. Therefore, this is going to infinity. That's how I saw it. Now, there are other ways you could see it, right? Some of you just plug numbers in, right, for a little bit. That would, you know, if I had devoted 10% of your test, right, 10% of the test's credit to you showing your work here, plugging numbers in isn't going to work for me. I'm going to need to see something more like this, right? But if this was part of a larger, like, you know, limit set, like the problem above, where I just was wanting to see the answer, then plugging numbers in will work just fine for you, right? So this is, as a first defense, think about plugging numbers in, right, and study patterns. As a second, more, you know, to give a more robust answer, a complete answer, you want to come up with some kind of like argument which no one can refuse you, right? I mean, certainly if the sequence is larger than n, it has to blow up, right? There are other arguments. This is just the one I found at the moment. Yeah.
So was that like a specific test, or is that just you kind of like showing?
You know, I haven't really labeled it as a theorem or anything. Like, this is a sequence, just a sort of a. I think we might have had a comparison theorem for sequences. I think it would be that one, if anything.
So you would like write out anything as long as you can.
No, if you can show me the estimate that your sequence is larger than a sequence which clearly diverges, then that implies that the sequence diverges. That'll suffice.
Okay, I just wanted to like make sure.
Right. So like on the flip side of things, yes, fair enough. So like with the series thing, if it's a series that you're, you know, studying the divergence or convergence of, I do like to see you say by the direct comparison test. We have a name for it, so if you cite it there, that there is admittedly there's an asymmetry here in my legalism for your mathematical conduct, right? I mean, like, I'm less of a Pharisee here, right? I'm much more Pharisaical in my insistence of you, you know, wearing the scripture on your forehead and also on your, you know, where do we put it? Right hand. Okay, anyway, this one here, nobody proved. Some of you saw that the limit was 3. Good for you. But if you plug numbers in, you can see relatively quickly that it's definitely going to go to 3, right? To prove that, you need to show it's a bounded monotonic sequence. To do that, I used induction to see that 3 was an upper bound. Obviously 0 is a lower bound, and I think I've neglected to show that it's decreasing. That's missing from the solution. So my solutions, you should take off like probably 20 decipoints from this solution. I don't know, something like that. But you know, to be fussy, we should show it's bounded, either decreasing or increasing, right? Once you have that, by the bounded monotonic sequence theorem, the sequence converges, and that means that you can take the limit of the recursion relation, and then you can solve for the limit, which turns out to be 3 here. So let me not dwell on that. I actually kind of like this style of problem for like a subset of your test where I sort of free you from the burden of writing down your reasoning, and I just say I want the answer, converge or diverge, right? So that does give me some information about students, right? There are some students who can do this who can't explain themselves, and so I'll try to have at least one question on the test where I have this kind of lightning round. You don't have to explain yourself, you just say converge or diverge, all right? So I have put the explanations here nonetheless just to try to explain to you how I knew they converged, okay? But I just graded this one on whether you said converge or diverge, pretty much. Unless you wrote something that was just very wrong and I felt like I had to take off points because it was just But maybe I didn't do that. I don't know. Anyway, so the first one, you take the limit as k goes to infinity, you get 1. That's not equal to 0, so the series diverges by kth term test. This one here is essentially the p equals 3/2 series, which means it converges since p is greater than 1. I will say this, if you were going to show your work here, you could use the limit comparison test. That probably would work, right? I would say limit comparison test is the way to go. This one, if you're going to show your work, I would use the alternating series test here. This one converges. This one is alternating, but it does not converge because the limit of inverse tangent as you feed something really large to it is pi over 2, right? So this goes to, it oscillates between 2 over pi and minus 2 over pi, which means it diverges. Again, essentially by the kth term test. This one is comparable. You can use direct comparison to the geometric series. See, because I can drop off a positive term in the denominator. So this is directly comparable to the geometric series, which converges to 4, in fact. So there's that. Some of you here, you just wrote diverge or converge. Like, that's not good. I said carefully calculate the sum of the series. That means, it means what it says. Carefully calculate the sum. So you have to work out what it is. And so there pretty much is only 3 things at your disposal for this, right? Either the geometric series result, or it telescopes, or it's a Riemann integral, right? So these are clearly not the Riemann integral form, so we're forced to conclude it's either telescoping or geometric. This one's straight up telescoping because if you do the partial fractions, you get this. Sorry about that, I put the minus here, I should have put it here, you know, so I put it out here in the end. So this calculation seems strange to you. It's because I added the minus after I realized that I was getting a negative answer, which was nonsense. Because obviously this is a positive series, right? You can't add up positive terms and get a negative result, right? Even in this fancy schmancy new series world, it's still the case. So anyway, everything cancels here except for like the 1/2 and the third, which ends up giving you 5/12. This one, you just got to use your imagination, factor out a 9. You've got e squared over 9 to the n power by laws of exponents, which we all know, or are still learning possibly. Let's see here, but that's okay. Just learn them before the test. And 9 over 1 minus that is the geometric series result, which you will be able to prove tomorrow on the test, right? Yes? Okay, good. So that converges to this. That works out to like 58 point something or other. So problem 11 is actually really easy because all you have to do is recognize this is an alternating series, plus minus, plus minus, plus minus. The error in the alternating series is bounded by the next term that you don't use as magnitude. So if I want to make the error at most 0.01, I just need to look at these terms and find the first term that's smaller than 0.01. That's 5 factorial, because 5 factorial is 1 over 120, which is 0.00833333, which is smaller. So in other words, just keep the first 2 terms. That's all you need to do. It was simple as that. Of course, I can make it more interesting by, like actually making you solve an inequality to figure out the end kind of thing. But as a first attack, I always just like plug numbers into it and see where the numbers get smaller than the error. It's usually not a lot of calculation to do that, Let's see here. This one diverges. Let's see here. I don't think it's immediately obvious why, because it's not immediately obvious why, because you've got something that's going to infinity like a lot upstairs, and that's going to infinity a lot downstairs. Which one wins? I don't think it's obvious from the outset. I have work shown on a separate page. We'll get to it. This one here is directly comparable to the harmonic series, therefore it diverges. See, because I'm dropping out something that's negative. Notice that inverse tangent is between 1 and 2. If we look at the inputs from the natural numbers, like inverse tangent gets to pi over 2, which is 1.57 eventually, but inverse tangent never gets beyond 2. And so like this denominator is, I think, smallest at 1. No, wait a minute. I think it's smallest at 1, and then I think it gets progressively, well, I don't want to say smaller. what I'm trying to say is this denominator is not, it's always positive, okay? There's nothing to worry about there. So we are dealing with a positive series. And so if I don't subtract that, that makes the denominator smaller, which makes the fraction larger, but then that's the 1 over n, which when I add it up from 1 to infinity gives me the t equals 1 series. So by direct comparison, I can see that this diverges. And so like intuition here, you're looking at it, and you've got basically n over n squared, right? And then you've got this thing, which is going to pi over 2. So what happens as n goes to infinity, essentially, is this is irrelevant, right? So you can basically just focus on the n over n squared piece. And I think if you did limit comparison to 1 over n, that might work here, if the direct comparison isn't working for you. But I found that direct comparison is a useful, simple argument for a lot of things. Problem 14 we'll talk about separately. Problem 15 was actually not that hard. It just looks formidable. So if I differentiate this, I can see that I get that, which is less than or equal to 0. That tells me that f decreases, which is to say it can't turn around, right? Well, notice that f of 1 is minus 1. So that means that f of n, which is log n minus the pth root of n, that also has to be negative, right? If it starts out at minus 1 and that expression's decreasing, it stays negative, right? That's the idea here. It stays negative. So since f of 1 is minus 1, f of n is also negative, which is all I need, because then that gives me that the natural log of n is less than the pth root of n, which then I can replace the denominator with the log with the pth root, and that is doing what? That is making the denominator what? Larger, which makes the fraction smaller, right? And then these are natural enemies. They, the pth root and the pth power, they annihilate in a flash of poof, and that leaves you 1 over n. And that diverges by the, when we add that up, we do direct comparison to the p equals 1 harmonic series, we get divergent. Yeah.
Correct me if I'm wrong. Isn't the natural log of 1 0?
It is.
So if you have the natural log of 1 being 0, you're going to infinity.
The natural log of 1, oh, yes, fair enough. I should put a 2 here, but
So
yeah.
just not exist.
Yeah, the series is ill-defined. If that's what you said, then I should give you points. Is that what you said?
No, I just went back and did it later.
Oh, okay. Yeah, technically speaking, you all should have been like, hey, dude, you can't do that. That's not cool. And also, another thing for cause for concern here is I've used a k here, but an n here. Come on. What the what? That's no good. Sorry. So let us make this n equals 2 to infinity. That would make this a more reasonable problem. Yeah. Sorry about that. Hopefully I won't do that on the test and thus make that problem omitted. Yes.
2 things. One, should we study this so we can have it for the test?
Is this a good example of what the test will be, except for the geometric series?
You want to understand the material. So if this helps you understand the material, then yes. If not, then no.
Could we go
Yeah.
over the geometric series?
Yeah, of course. So,
Will you post in the solution?
yeah, I will post a solution to this after class. So here,
Where do you post those solutions?
Canvas.
I can find it. Okay.
Canvas. I hide them in Canvas. Let's see here. If you can't find a solution for something, just email me. I'll help you. Now, so this is for problem 12. There is something important here. I should clarify. The ratio test does apply when you get infinity. I don't know if I ever came out and said this. I don't think it's in my examples, but it should be mentioned. If the ratio test works out to infinity, it implies divergent. If you look at the argument that we have for when the ratio test works out to something, the row works out to larger than 1, that argument can easily be adapted to show that if the row is going to infinity, that likewise implies that your series is unbounded, and your series will diverge by the kth term test, right? So let's just simplify our life and make that part of our ratio test. If the ratio works out to infinity, you can say it diverges, right? In case you were unclear about that. I'm not sure I ever said it, so at this point in problem 12, so what I'm saying is in problem 12, my solution here, I could stop right here and go, okay, this works out to infinity, therefore that series, the original series, diverges, all right? And then this argument down here shows you that you didn't really need to do the ratio test, right? You could have actually just looked at 2k factorial over k to the k, and if you look at that, you got a bunch of k's, right? 2k all the way down to k plus 1, and then you got k times, well, you got a k factorial left over here, right? And if I divide by 2k minus 1, divide by k plus 1, what am I doing? I'm making the denominator larger, which would make these all cancel out to 1, and that would just leave me the last bunch here, which is k factorial. In other words, this expression is larger than k factorial. What happens to k factorial as k goes to infinity? It goes to infinity, like a lot, right? So this is definitely diverging to infinity. It does not go to 0, therefore by the kth term test, you can see that this series is not convergent. I'm saying, so there's two ways to do this problem. You could either use the kth term test, or you could do the ratio test and see the ratio goes to infinity. Yeah.
The alternating series test also.
Well, the alternating series test in the, I would say that the alternating, I don't really use the alternating series test when it diverges. To me, I mean, you could, does your alternating series test have a divergent case in it?
It works out.
Okay.
The limit goes to diverge as well.
So that's part of mine. Okay, then that's also fine. Yeah. Of course, that's proved with the kth term test, right? So it's like, yeah. So it's like, I don't know. This one here, 2 to the n squared over n factorial. If we look at the ratio test, n plus 1 squared is n squared plus 2n plus 1. And this n plus 1 factorial splits like that. So this 2 to the n squared and that n squared cancel. The n factorials cancel. It leaves me 2 to the n plus 1 over n plus 1. Now that is ambiguous because it's infinity over infinity. But we can resolve that limit using Lhopitals rule, extending n continuously like so. And we get that it's clearly infinity. Therefore, the ratio test goes to infinity. Therefore, this series diverges, is a way you could have done that one. All right, so yes, I will post this here after class.
When we're doing Lhopitals rule, should we say like 0 over 0 or infinity over infinity?
That would be good.
And also, what is the like Lhopitals rule? Our the last teacher I had told us we had to like put Lhop. So like what
Yep.
would you like us to do for that?
You could put Lhop, or you could spell it out if you wanted, or you can write the script L through the thing with the 0 over 0 or infinity over infinity. Like, I don't care, as long as you say something. You know, say something.
Give a short biography of Lhopitals.
You can be. This is not actually Lhopitals rule. L'Hopital is merely the author of a popular calculus book in the early 19th century, which he is improperly given credit for this rule. It's actually probably due to one of the Bernoullis.
Didn't we pay one of the Bernoullis to write the book for him?
That sounds plausible. Let's see here. I'm finding my way back to. So if you look in Canvas, and I don't generally recommend that, I have solutions posted for like the quizzes and all kinds of stuff in here, right? Test 1 solutions posted in there. The Java files you guys can't open is posted in there. The solution to mission 2 is posted in there.
Are you going to put your sequence series onto your website?
Yeah, I will. I haven't yet. True that is. All right. I really dislike the way Canvas works. Did I mention that?
No.
Oh, okay. Oh, that's unusually positive of me. See here. Okay, good. I did post the solution to quiz 5. It's also there. What I'm trying to find, there it is. So you asked me about the proof of the geometric series. It's in here. We talked about it in class. It's pretty it's actually really easy to learn. And so what did I say in the announcement in terms of proofs? Like what are the theorems that I hold you responsible for? They're the ones that were also homework problems, right? So you should be able to prove like the sum of the limits is the limit of the sum, right? That one you actually need to know the definition of the sequential limit to be successful at, right? That was the one where we did epsilon over 2 for each. We picked n to be the maximum of n sub a and n sub b, all that. That was a homework problem. So the proofs which are in mission 2 could also be on the test. I'll just say that. Now, I did, on the other hand, I promised you, wait, where'd it go? I guess I put it up here.
You need to know the definition of a sequential limit.
That is true, yeah. So that's right at the start of all this. But here's the proof of the geometric series. It's just this. You write down Sn, write down the nth partial sum, then you multiply by r, all right? Then you subtract them. See that everything cancels except for like 2 terms. And then you can solve for Sn. You get Sn as this, right? And then you take the limit as n goes to infinity. In the case that the absolute value of r is less than 1, you get that this goes to c over 1 minus r, which of course is the geometric series result. And otherwise it blows up, yeah.
Are you always going to give us geometric series starting at k equals 0, or will it be like a k equals 1?
For the proof or for the...
Yeah. That makes the first term different. This starts at 1.
Well, yeah, but I start at 0, so... Because I have said that the first term is c, so if I say that, I guess I'm starting at 0, right?
Right.
But indeed, and I mean, if you want to get fussy, you'd be like, your nth partial sum is actually your n plus 1th partial sum here. So deal with that, right? And I have worried about this in past semesters, but I've come to the conclusion that I'm the only one worrying about it, so I stopped. So, yeah. I just call it S sub n. It is sometimes not literally the nth partial sum, though. That is true. So let me get out of here and go back to my mission 2. So, like, what am I talking about in mission 2? So you asked me what I should study. Well, I think you should study mission 2, among other things. You know, I had a bunch of integration, solved differential equations. We have spent very little time talking about differential equations today, right? But it is 40% of the test. I just think that you guys have a much easier time with that material than the sequences in series. Therefore, I focus on the part that I think is going to get you, right? But part of the reason that I have saved differential equation for test 2 is to try to help your help your grade. Yes?
Will you by any chance have any p-plane stuff like on the...
It's possible.
Because I can't really use it on my computer because it just doesn't work. I have Java installed and everything. It just doesn't work.
Yeah, well, that should be, I mean, you can read the notes though, right? And the notes has commentary on, like, you know, how the direction field, what it means and how to understand it, so.
Yeah, it doesn't run for me.
That's okay, I mean, but you guys do have a course, in my defense, you guys do have a course in MATLAB. You should be able to run p-plane in MATLAB. You're not taking MATLAB till junior year?
Hey, I'm taking it over the summer.
You guys are hoping it goes away or something? Trying to procrastinate your way out of it? Interesting approach. I procrastinated my way out of learning, I procrastinated my way out of foreign languages in grad school.
Nice.
Yeah, they dropped it. I was like, whew, that was close. I thought I was going to have to learn more German. I had a year of German undergrad. I mostly just know this. Ich verstehe nicht. Means I don't understand in German. Let's see here. So, which is a fun thing to say with Germans in an elevator. So you got to know your integrating factor. All right. So do study those. I will say this, if there's a substitution problem on the test, I will suggest the substitution for you. I think I did that on the math battle, didn't I? I said to solve y prime prime minus y equal to 0, make a v equals y prime substitution. I think I said that. I think I did say that. Here is the problem right here that is like the math battle problem that none of you did. So I make the substitution, do the v dv dy trick, solve, separate, right? Separate, integrate, and then I have to solve for v. And solving for v ends up giving me like a square root integral, which you can solve with an inverse sine. And then to solve for w, I take the sine of both sides. And then trigonometry gets me to c1 cosine t, c1 sine t plus c2 cosine t. It turns out that when you do the same calculation with that plus being a minus, you get sinh and cos here, which I don't know, I think is neat. You can disagree with me if you want, but problem 59, I would have given you guys a hint on that if you'd asked me about it, but oh well. Problem 60 is not bad actually, but let's see here. So let me just scooch ahead here a bit. Man, this problem was so annoying. Let's see here. There is always a problem that is nth term test on my test too. There will be one that's nth term test. So look for that. If you can see it, then you get that one, right? How do you work the nth term test problem? Take the limit of the nth term, and if it's not, or the kth term, and if it's not equal to 0, then it diverges by the kth term test. Now, let's see here. Sorry, I'm trying to flip ahead here to the proofs I was blathering on about. Where'd they go?
It's like 87 or 89.
So here, so here's the, the proof that the limit of a sum is the sum of the limits. You should look at this. It's a problem in your homework. I spent 20 minutes of class time on it. It could be on the test. It's possible. In class, I combined A and B into one argument.
Is that acceptable on the test?
Yeah. If a logical argument will work. So another thing that I might ask you to prove on the test is the nth term test. Here's the proof of the nth term test right here, right? It's really simple. You just take the difference of the n and n minus 1th partial sums. It gives you the nth term. So if we take the limit as n goes to infinity, if this exists, well, that limits to s minus s, which is 0. So must this also limit to 0. That's the nth term test. That's the proof of it. It's very simple. And also the proof that the limit of the series, if you have a, two convergent series, the sum of the series is the sum of the series of the sums rather, like this. So here you have to have clear in your mind the definition of series as it relates to partial sums, and then if you also know the sequential addition theorem, then you use it together and you get this. I mean, it's not bad, but yes, sir.
Is the nth term test the same as the kth term test?
Yes, yeah. It's just you can make it the mth term if you want to use m instead or whatever. Okay. Anyway, I think that's it. So I'll see you guys tomorrow. Yep.
89.
89.